Hi everyone, this is Kirsten Rooklas with NASEO. Thank you for joining us for the webinar on Integrated Resilient Distribution Planning. We will start in just a moment. Hi everyone, this is Kirsten Rooklas, Program Director for Electricity at the National Association of State Energy Officials. Thank you for joining us for the NARUC NASEO Task Force on Comprehensive Electricity Planning on Integrated Resilient Distribution Planning webinar. We are joined today by moderator Sushma Masmore from the North Carolina Department of Environmental Quality and Paul DiBartini, who's giving the presentation from Newport Consulting Group, LLC. Before we get started, I just wanted to go over a few housekeeping rules. This webinar is recorded. If all participants are muted, if you want to ask a question, questions can be asked in the question box. You can see there a mock-up of the GoToWebinar setup, and you can type in the questions in the question box, and we will get to your questions at the end of the webinar. With that, I would like to introduce our moderator for today, Sushma Masmore. She's the Deputy Assistant Secretary for the Environment and the State Energy Director at the North Carolina Department of Environmental Quality. She was named the Deputy Assistant Secretary in 2018 and State Energy Director in 2019. She works to bring clean energy solutions and sustainable practices to North Carolina businesses, citizens, and government operations. For the State Energy Office, Sushma oversees programs related to low-income weatherization assistance, energy planning, energy efficiency, and transportation alternatives. She's leading statewide initiatives related to climate change impacts, adaptation, and resiliency. Sushma has 29 years of public and private sector experience related to pollution control and energy systems planning. She earned her BS in chemical engineering from University of Maryland, Baltimore County, and is a licensed professional engineer in North Carolina. Over to you, Sushma.
Thanks, Kirsten. Good afternoon, everyone. Today, it's my pleasure to introduce Paul DiBartini. Paul is a leading expert on the business, policy, and technology dimensions of a more distributed power system. He works with utility market operators, regulatory, and government clients globally. And over the past 8 years, Paul has supported grid transformation and modernization efforts in Australia, Canada, and in the US. And this includes supporting 12 of the 15 largest electric utilities, over 10 state regulatory commissions, and 3 of the world's largest grid operators. Paul has authored and co-authored several seminal reports that have become widely cited, including several US DOE reports. And some of them you may have heard of. That includes the SPX Modern Distribution Grid Report, Integrated Distribution Planning, and T&D Operational Coordination Framework. Paul was previously the Chief Technology and Strategy Officer, Energy Internet of Things at Cisco Systems, and Vice President, Advanced Technology at Southern California Edison. He began his career at PG&E in electric system operations, T&D engineering and construction, and wholesale markets. Currently, Paul is a visiting scholar at Caltech and adjunct professor at the University of San Francisco. Paul holds an MBA from University of Southern California, a BS in Applied Economics from University of San Francisco, and a certificate in Technology Management from Caltech. Paul is also a California State Certified Electric Systems Operator. So with that, Paul, please get started.
Thank you so much, and glad to join everyone today and share a few thoughts on the work that we've been doing as part of several efforts within the Department of Energy's Office of Electricity in thinking about distribution planning and its evolution, going back to the work that we did in Minnesota and other states earlier and how we've evolved our thinking, particularly as we've started to incorporate resilience dimensions and considering how we tie that into the integrated distribution planning process that we've been developing over time. So today's presentation is some of our current thinking on how we build on some of our prior work, and we're still in a work in progress, so more to discuss today than to have sort of concrete, this is how it's done. So much more, discussion about how we might evolve, how we might tie some of these threads together into an integrated planning process. So with that, let me go to slide 2. Thank you. As we're discussing with integrated distribution planning, there are really 3 principal areas that we think about in sort of these buckets. One is reliability and resilience, another is DER integration and utilization, and another is the very fundamental safety and operational efficiency dimensions. And those 3 domains essentially align to 3 different planning processes that are done typically within a utility, a resilience and reliability planning thread, an asset planning, asset management thread, and a grid expansion or upgrade and modernization planning. And we'll touch on all 3 of these and how we think that they can start to be integrated more completely into a kind of a unified distribution plan, one that then can be looked at in terms of potential optimization and how customer or third-party solutions might be part of the mix in terms of the solution set. Also, we'll touch on how other elements within overall planning, within resource planning and transmission planning, touch on these as well. But we'll primarily focus on the distribution dimensions today. Next slide, please. So on this slide, what we're trying to describe here is that planning at the distribution level has pretty much similar, whether we're looking at asset planning or whether we're looking at grid expansion or modernization or even resilience, reliability planning. There are multiple steps that tend to be the same sort of generic steps. It's just that what we do in terms of planning analysis or criteria and the needs identification, they tend to be a bit different. And by the way, these steps in the blue, light blue at the front end are pretty similar to the steps that I've seen that you all have been developing as part of your comprehensive system planning. So they're pretty similar in terms of the even naming, but they're very consistent with that. I would say the one area that we've been also exploring is a piece that I haven't seen on your diagrams, and that's the system evaluation. So that is, once you do the planning and the implementation, then you look at how things perform, and then there's an evaluation that then feeds back into your objectives and criteria and planning analysis. But we'll tend to focus on the front end of this today. Next slide, please. So there's a lot going on this slide, but what was intended was start to look at how we might think about the integration of these different analyses that are done largely outside the distribution planning process, and at least conceptually where the linkage is, say with an IRP process as part of an input into both objectives and planning criteria, to the extent that there are incremental DER that are identified as supporting what may be required in terms of capacity expansion or replacement of resources to meet resource objectives. So how DER may be identified in the IRP process for that. And then also the other thread there where feeding into load and DER forecast is that system level DER forecast that feeds into a top-down, bottom-up analysis into the distribution, more granular forecasting. So that's what's represented there. In terms of threat assessment, increasingly a number of areas have been having ongoing discussions at the state level and engaging utilities in looking at various threats that would or could potentially or have happened in those areas, and starting to look at doing very specific threat assessments, and the results of those start to feed into planning objectives and in effect some criteria that go into distribution level planning, and we'll talk more about that. Obviously, there are other planning objectives, things like transportation electrification, how microgrids and the like might feed in and support resilience objectives. Obviously, affordability is pretty universal, and there are typically other policies and standards that come into play that performance standards for what the distribution system service needs to adhere to. Those also feed into this process. So that's on the front end, and then as we get into this, we'll talk a little bit more about each of these dimensions. Next slide, please. So here we wanted to, and we've been having a discussion with folks, and so we wanted to kind of set the context for how the team working with Johanna Zetterberg and Joe Palladino, we've been looking at this question of reliability and resilience, and there's a lot of discussion about terminology and definitions. And what we started looking at was recognizing that in practice, that really the way that we plan about the distribution system is that there are really fundamentally two types of events. Those events that are less than 24 hours and in terms of scope are not identified as a major event. That is more typical sort of say a car pole accident creating a local outage, fuse blows on a transformer, a single wire down that causes a local outage, or even if it's a little larger area involved, it's not a very long duration. So we've kind of boxed that in that gray box at the lower left, with the idea that we pretty much understand those kinds of events. The ICE calculator, for example, goes up to 24 hours. The IEEE standard 1366 has the metrics for things like SAIDI, CAIDI, system average interruption duration index, and the customer version of that, as you're probably familiar. Those all fit within the gray box. So everything beyond that, either in terms of scale and scope, which would be deemed a major event under the standard, or longer than 24 hours, we're considering a resiliency event. We'll get into more of this. The red line represents that what we've seen in past major events is that the economic and social impacts grow over time as the duration and the severity of the event in terms of scale and scope. And we know that it's not linear, it's exponential in terms of the economic and social impact. And so this is just conceptually a way for us to think about how we might approach this from a planning standpoint and understand that there's this continuity. The other thing at distribution to kind of keep in mind is the kind of things that break on the distribution system are the same things that happen when it's small outage, what we would consider a reliability event, as would happen in a resiliency event. It's just that there's lots more of those things that are breaking or failing potentially, whether we're talking about poles breaking, transformer failure, fuses blown, wire down. When we're talking about a resiliency event, we have a lot of that widespread, and it takes longer time to restore all that, which creates this outage duration. In a reliability event, we can have the same thing, but now we're talking about a single pole, single transformer, or the like. So that's the distinction there. But it has an implication for planning, as I said. On the next slide, what we wanted to introduce is what we're calling the Maslow's hierarchy of grid investments, if you will. And that is that as we think about the kinds of investments that are made by a utility in the distribution system, there tends to be a hierarchy of a priority in terms of where the money is spent, starting with the dark blue areas and looking at fundamentally addressing in this sort of Maslow's hierarchy, basic safety and electric code compliance, then focused on a resilient and reliable distribution system, that the way that the system is designed, configured, and then obviously looking at preparedness, and then obviously a focus on aging infrastructure replacement, and often hardening as goes along with that, depending on the nature of the threats in that particular area, with the idea that you're creating this fundamental foundation of a robust grid to be able to support everything that goes on top of it. So then we move up this pyramid into the next layer, which is distribution automation, and then we get into more advanced grid modernization technologies, and then being able to have technologies that can then support greater very large scale DER integration and utilization, and microgrids, whether we're talking about customer microgrids that are synchronizing to the system, or we're talking about community-based multi-user microgrids, which are quite sophisticated. And as we look over to the side there, what we're illustrating is that where the focus of the different planning efforts that often in the past may have been done by different groups within a utility, where you have asset planning that tends to focus on the first 4 layers, you have resilience and reliability planning that tends to cover a lot of the spectrum in effect, and then you have grid modernization that tends to focus on the top part of the pyramid in many cases. It may also extend down to basic distribution automation. But we tend to have different lenses by which these different planning efforts look at things. And what we're suggesting as we look at this going forward is, from an integrated distribution, is we need to really kind of understand all these elements. And the reason is that if we go to the next slide, thank you, is that when you look at a typical capital budget allocation for a utility, you will see in this pie that almost everything is shaded a color blue except the public works relocation, which is moving a line from one side of the, or pole from one side of the street to the other side of the street because of some street widening. Almost everything else touches on reliability and resilience. That is what is invested in to address those particular buckets or wedges of the pie, essentially have some implication on the ability of that system, depending on what decision is made in that wedge, in terms of what technology or infrastructure is built, has some implication on reliability and resilience. So it's quite important from our view that we really understand holistically what is desired from that perspective, from a resilience perspective, so that we can understand how that needs to tie into these other elements, and vice versa. So how can we have an optimal set of solutions as we think about how to address these different kind of categories. And I haven't forgotten about the role that customers and third parties play in this, but just to set the context of the kind of wedges in the relationship and overlapping relationships. Next slide, please. And here I'm just reinforcing exactly that point, that we have essentially with distribution now, which is quite different than where we were even a decade ago and certainly 15 years ago. We really have a much more complex set of planning objectives that we're trying to accomplish. If we start with those 3 circles that I showed earlier, and now we start to add a little bit more specifically, we drill down a little bit and we start thinking about discussions that are going on in a number of states around how to think about electrification or what to do with aging distribution infrastructure, how customer solar and storage adoption is happening, the role that community microgrids may be playing, or how communities may be anticipating a role there to address what they perceive as their local resilience needs, the role that customers are, what they're doing in terms of essentially creating their own self-reliance model with their own backup generation or microgrid or backup storage. So how these are all starting to create quite a unique set of objectives that need to be thought about. And as we think about the planning process, the question starts to become, how do we distinguish between those areas that are not overlapping with those areas there are overlapping, and are there opportunities to think about the needs coming out of the planning analysis that then we, what are those solutions that might satisfy the majority of these needs. Let me give you just a quick example. A couple months ago, the California Public Utility Commission issued a proposed decision as part of the wildfire mitigation planning process, and as part of that, the preventative power shutdown. And in that, the commission, ordered PG&E as part of their preventative shutdown plan to not only address what they thought in terms of kind of just focusing on, say, community microgrid kind of capability, but at the same time that any solution that would be developed to address sort of the backup power options, or including microgrid, that they also consider that how they would address blue sky opportunities to support electrification and additional customer solar plus storage options and other objectives that the state has. So not be so focused just on what happens when there's an outage, but also anything that's getting built out for that or planned for it needs to also consider these other objectives at the same time. It's one example of where I think we're looking to head as we move forward this decade, that there's multiple objectives that are going to need to be addressed in the planning process in a way that really haven't happened exactly this way yet. There's certainly been some efforts to do this, but I think more concretely, based on a lot of the feedback and interest that I've heard from several of you as I've had interaction through some of the training, it's pretty clear I think we're heading in this sort of direction. I think the next slide, I can't remember where we're at in the next slide. Yeah, one more slide. So some of you may be familiar with the work that I did for Minnesota quite a few years ago, looking at integrated distribution planning in the paper for ICF that was sponsored by the DOE, and in that paper we had a version of this, and I've updated this to basically add in the resilience analysis and also the distribution asset management or asset planning inside that light blue shaded box. I've also added a couple of other pieces and then tied basically the planning steps to those different parts of the diagram. That is kind of a complex diagram to kind of highlight where we are on that process flow. I only provide this as reference. We will be looking at specific aspects of kind of come back up from this and go through each of the steps in the next slides. But we wanted to pause here and see if there's any clarifying questions before we go into the next phase.
Thanks, Paul. As many of the participants have been involved in the NARUC NASEO task force, they each has been working amongst their cohorts to evaluate different methods of incorporating transmission resource distribution planning. So looking at it from their perspective of what they have accomplished thus far in T&D and G planning, how does resilient distribution planning align with transmission and resource planning? Can you speak to that?
Yeah, so first, in terms of resilience planning, the resilience kind of threat assessment that I was describing is done at a level above the power system, if you will. So it's looking more holistically across an area, whether it's at a state level or a county level or even a city level, and it's part of that process that typically a state leads, and as part of that, often a utility will be part of a piece to look at specifically the power system, given that the power system is by and large the lifeblood of our modern economy and society. So the implications of having a resilient electric system are quite important, as we all know. So as part of that, you then start to come and look at the power system. But when you first start to look at that, there is a dimension of that resilience when we think about those threats that have been identified. Then you look at the implication that it might have on resources in terms of their ability to produce power. the transmission system in terms of its functions, and obviously the way it's structured and various assets. Same thing with the resource, and the same thing extends to the distribution. So you're starting with the same basic input in terms of here are the potential threats for a particular area, and then really we dive into, well, given those events, then what may happen in terms of things that may break or fail. So each starts from the same place, but each will have its own unique implications with respect to what may fail. What may fail on the distribution is not going to be necessarily have any implication on what fails at, say, a generator or fails at the transmission. But you do start with a common set of inputs in terms of, magnitude of events or the probability of event or the type of event and scale and scope and so on. At the end, yeah, go ahead.
A quick follow-up on that is when you say that the same set of threat assessments are used in those different aspects of planning, does that mean that those threat assessments or hazard identification are uniform and accepted and or recognized in order to accomplish those objectives?
You would want to have that, so there's consistency. This is my personal view. I think you'd want to have consistency in terms of how that threat was looked at, so that you, and again, I think there's a role here for the state, or county, agencies that are responsible for, identifying and developing these threat assessments. At the level of determining what threats may occur, so that you have consistency across these different planning domains. So everybody's starting with the same assumptions as to what the potential threat is. Now, then looking at the impact assessment, the impact assessments will be different for each of those planning processes because there's different assets involved and different locations. But yes, you do want to start, I think, with the same common threat assessment for a particular geographic area.
Okay. Thank you. I don't see any other questions, so we can move on and look at the questions later.
And we were just talking about this, so good timing. So in this case, the graphic is really there just for a quick illustration, but there was a nice one that was developed by the Hawaiian Electric Resilience Stakeholder Working Group, and they have a report that's coming out. But there's a number, and I included a link to their website at the end of this presentation for those who may be interested. But they aren't the only place that have done this kind of analysis. But building on that state level kind of assessment, and for each island, then they started working with other stakeholders to then start to look at the potential impact in the context of starting to feed into both resource transmission and distribution planning. So that's what that activity was about. The issue now is how do you translate that into specific, sort of guidance and thinking about planning analysis and impact assessment and so on. And that gets tricky because as you can imagine, events, even though we might say hurricane is the top event, there's lots of different scales of hurricane. They may hit different geographic parts of a particular area. And so therefore, the scale of that event can really dramatically change. So as we think about, as illustrated in the lower right, moving beyond reliability events, then we might have something that's more of a local event, something that extends beyond kind of that to maybe, a whole service territory for a particular utility. And obviously we've seen some pretty major regional events where we're talking about multi-state events. And so how to think about this scale and the implications as we start to then think about the planning process. So another piece is to really sort of unpack that distribution resilience to kind of gain some insights into what may be needed. Next slide, please. This kind of goes without saying, but obviously critical infrastructure interdependencies is really important. And I think as we get further into understanding this through these conversations that have been ongoing now for the better part of a decade, as we've seen more and more major events, I think there's a better understanding. This also extends to defense critical facilities, as some of you have probably been part of those conversations, and that's certainly an interest of the Department of Energy in ensuring, from a national defense and even civil defense, really understanding what are those critical facilities, how does this infrastructure need to be able to support, the society, in that area, that community, and what is the role of electricity in that, and looking very specifically at those threads. So whether we're talking about electricity for communications that are necessary for, maintaining, just communication with the society. I can speak to, my own experience where I live in Northern California, when we had some of these outages over the last couple of years, the cellular communications dropped, and the NIXL system that the emergency services for the counties use to communicate with people through their cell phones was not available. So evacuation orders for wildfires were not getting through. So it's a pretty big issue of understanding how electricity not just services the water, facility or sewer treatment plant, but, certainly communications and understanding those dimensions, and then therefore, how do we think about what needs to be the resilient solution for those different dimensions. So this sort of diagram is just one way of kind of thinking about the kind of implication that at a very granular level, how these things tie together. Next slide, please. Now, there are two ways that people tend to think about resilience, and I'll show this on the next slide. But here, one dimension of resilience is the ability to withstand the impact. So your ability to resist a certain amount of stress, and the other is the strain. These are sort of engineering dimensions that my colleague Jeff Taft has talked about, and so this is clearly one part of this. What is your defense against that potential impact? How do you ensure that the system doesn't break? Now, the second part of resilience that people tend to talk about is, okay, if it does break or parts of it break, then what's your response to that? How do you mitigate that breakage, the impact of that breakage, if you will, and how quickly can you restore to put the system back together and restore power to everyone? So there's really kind of two dimensions that people talk about. From a strictly architectural piece, there's this sort of stress resistance and strain compensation, and then there's this responsive piece. We highlight this resilience piece here because often this doesn't get as much discussion, particularly when we think beyond the hardness dimension, which does get a fair amount of discussion, but there's these other pieces about how we might think from an engineering standpoint to develop solutions to address this need. And then obviously there's a lot of focus on restoration and so on. We won't get too much into that, but next slide, please. So here, one of the things, and I don't know how much folks are familiar with this, but one of the things that a number of locations have been doing, certainly there were a number of utilities, post the Superstorm Sandy and currently in California, have been looking at and applying a technique called the bow tie threat risk mitigation analysis. And the idea is that you take that threat analysis that we talked about earlier that would be done at a state level, or then maybe further refined through a process like what Hawaiian Electric did with multiple stakeholders, including the state agencies. And then you develop these, you identify these physical and cyber vulnerabilities. We've kind of been focusing on physical vulnerabilities, but cyber vulnerabilities are also important to consider. And then within that, we identify those solutions to prevent that specific failure. So just what I was talking about before, can you develop defenses that mitigate that initial impact from that event? But then if there is, and that's done for a specific type of failure. In this case, as an example, substation transformer failure. Assuming that you come up with a set, but nothing's perfect, that you may in fact have a failure, then if your plan A doesn't work, which is that defense, then you need to develop a plan B, which is to mitigate the impacts of that event, that in this case, substation transformer failure. So then what are your solutions to mitigate that? And the idea is to develop a set of solutions that get you to a point at which the net impact after your mitigations, because you're still having an impact, but to the extent that you can mitigate that to some acceptable risk tolerance. So maybe some number of customers that still would be out, or whatever, or economic impact, or however you want to determine it. Basically, that starts to define your planning criteria for how you think about this, both on the front end and then on the back end of this second sort of Plan B analysis. So this is, for example, what's going on in California as they put together things like wildfire mitigation plans, is both looking at both sides of this equation. This is also what was done in New York by some of the utilities, if not all the utilities, in looking at Superstorm Sandy, where things like a specific failure was a transformer failure and due to flooding, and therefore there were solutions to defend against that, which was essentially putting concrete barriers around to prevent flooding of the transformer. But there were also Plan B options to mitigate if in fact flooding did occur, went even higher than that. Then what would you do to mitigate the potential outage that would otherwise occur? So this kind of analysis can get quite complex, and obviously you have to look at this for every kind of threat, and then also the kind of very specific types of failures that you may see on a system. So this can get pretty involved. Next slide, please. Just to illustrate, there are a couple things. It's a little hard to read here, but one is done, as I mentioned, this is in California. So one is the analysis that was done coming out of, I think it's SoCal Eds or PG&E's. And you can see that some of the consequences they look at are not just the outage, but they look at things like safety. They look at things like overall compliance issues. They do look at financial implications. They do look at a variety of different societal dimensions. And you can see that the other one, which is for Sacramento Municipal Utility District, has a similar thing. And they also look at a number of different risk factors that they're trying to mitigate. So this is like I said, it's pretty involved kind of analysis, but it's one that you can start to have a pretty thoughtful discussion about what the solutions are, what are you trying to mitigate, and how best to prioritize those solutions and related investments. But this is just one input into that solution development part. Next slide, please. So the other part that we're talking about is, so how do we think about DER and by extension, increasingly microgrid development? And this curve, you may have seen the earlier versions that I developed some years ago. And this has been updated to reflect a little bit better understanding of where we may be heading for stage 3. And in a number of states, we're already pretty well into stage 2, where we've been looking at increasing electrification. We certainly have community solar and storage. Customers certainly have been adopting greater numbers of distributed resources, solar and storage, starting to adopt much more storage and on-site generation for resilience. And we've started to see in a number of places both DER participating in wholesale markets or in areas that are vertically integrated, DER being used for grid services, for say non-wires alternatives, or at least exploring that. So in many places we've moved pretty well into stage 2 or starting to move into stage 2. In some states where we're really seeing a push for some at the community level for greater resilience, we're seeing more of this discussion around community multi-user microgrids. Now, what's meant by that is basically forming a microgrid in front of the meter by combining customer resources, perhaps a utility generator or storage, or an independent storage unit, and using the distribution system as a way to connect these different customers and resources to be able to form a microgrid and an islanded mode. These are very complex, but we're starting to see these developments. Hawaii has, there's a draft community microgrid tariff that has been filed in Hawaii. There's a proceeding in California that's pursuing this. We have in Illinois, there's an effort sort of as a adjunct to the Bronzeville microgrid project that was exploring this. Certainly in New York, the New York Prize effort was focused on these types of microgrids, and we've seen this kind of discussion in other places as well. We're also starting to see, as some states move beyond net energy metering tariffs, where the tariff actually has the sale of any excess energy back to a utility or load serving entity, in effect creating a buy-sell arrangement, and not unlike what already exists in Texas and in Hawaii, but we're seeing this in other places as well as alternatives to alternative rate designs. And in some cases, like in California, we're seeing some of the California community choice aggregators looking to distributed resources as meeting their resource adequacy and renewable targets, and therefore with the sort of export energy relationship. So the distribution system becoming a generation tie in effect. So we're starting to see much more discussion of what seemed pretty conceptual, pretty far out there a few years back. We're starting to actually see some of this, on the not too far horizon in a few places around the U.S. And that has implications for what we think about in terms of the distribution system and its function to meet that other bubble regarding DER integration and utilization. So it's not too soon to be thinking ahead where we might be over the balance of this decade, and particularly in a number of places where we're already starting to touch on some of these dimensions in regulatory orders and in what customers and others are developing or proposing to develop. So this is certainly an implication as we start to think ahead in terms of what the grid needs to do to support DER integration and utilization. Next slide, please. So coming back to how we think about forecasting, and in particular, distributed energy resource and load forecasting. As you probably are aware, and I'm sure you all have been talking about this, but at distribution, you don't use just literally the same forecast that is developed for integrated resource plan or by extension transmission. There's a need to look at this on a little more granular basis. And so you really combine both the what comes out of that top-down system forecast that's used in an IRP with a bottom-up locational analysis or adjustments, if you will, that factor in the locational dimensions that at a more granular level that you wouldn't get in a system level forecast. This is just one example from SoCal Ed, just to give you an illustration of how they go about it. A number of utilities do this now as they've seen greater amounts of distributed resource, and particularly as electrification with electric vehicles. It's really important to understand those nuances at the local level because it really matters on an individual circuit or substation transformer or substation itself. Zip codes alone are not going to get you the kind of information you need for distribution planning. So taking it a little further becomes pretty important. And there are a number of techniques here that are available that you can take a look at. This is just one example. Next slide, please. The other question that comes up a lot is how do we think about dealing with forecast uncertainty? Because one of the things that's a real challenge at the distribution level is because you're down at a very granular level, trying to understand, 5 to 10 years out, what's going to happen on a particular circuit becomes quite challenging because you may have new loads show up, you may have loads to go away as businesses close or move. You may have different rates of adoption, kind of start and stop, given events like we're experiencing, today. So being able to understand at that level becomes quite challenging. So one of the things that folks have been looking at for some time is how do we move beyond sort of level 1 type forecasts, which are kind of deterministic point forecasts that were kind of used pretty regularly in the past, with some modification based on near-term changes that people knew about, some new residential development or new commercial development, or changes in customer mix and the like. Now what we're thinking about and what people are looking at is level 2, kind of using these alternative futures or scenarios with sensitivities that allow you to kind of understand what some potential ranges of things that may happen or different outcomes that may happen through these different combinations of the sensitivities around things like electric vehicle adoption, solar plus storage, so on and so forth. So understanding how the mix of those might change the different outcomes. These are useful not to sort of then project what the needs and then start designing to build to that, but rather for stress testing your base case that you develop. So you develop this base case, and then you use these other sensitivities to really stress test what you're thinking that systems need and what may change under these different scenarios when you start to look further out in time. It's important to understand that in distribution, if you do a 10-year forecast, people are really only needing to start to build something, particularly a line extension or some other kind of more straightforward upgrade, about 3 years out. So so if you see something that may show up in year 8 or 9, typically that's utilities will not be proposing to invest for that, but rather that may be something that happens, but they'll keep an eye on it as they get closer to that time window in which they do need to start an engineering analysis to look at more specific solutions. Now, in some cases, a substation where you needed a new substation and it was going to require land acquisition and so on, now you're thinking about something that may have to be looked at 7 years out just because of the permitting process and approval process and development process. But that may be a bit unique in most cases anymore. More often than not, we're talking about shorter time periods for most investments. Next slide, please. Okay. I think in terms of system planning analysis, you all have seen this or maybe have talked about it. There are essentially 5 key aspects that are done. Thermal loading analysis, power quality analysis, which is largely centers on voltage, but there's some other aspects that will be considered as well. There's a protection analysis. There's usually a contingency analysis, which starts to factor into reliability and resilience dimensions. Contingency being, if there is an event, how do you then have the system reconfigure itself on distribution to be able to pick up that load or mitigate the impact, as we talked about in the resilience context. So that's what contingency analysis is. And then forecast hosting capacity. And this is a newer one where we're taking a longer term forecast, similar to what we talked about a moment ago, and then looking at the implication for hosting a range of different distributed resources on that system. I think as we go forward, as I touched on, to the extent that those resources are going to be contributing to the resource adequacy of that area as part of an integrated resource plan, as an energy resource into the system, not just a load modifying resource, this hosting capacity is going to be probably evolving into something that is done at transmission, which is called deliverability analysis. That is your ability to ensure that the energy from that edge can get delivered to wherever that TD interface is, usually at the high side of a transmission distribution substation. So, what is that deliverability between that point for meeting to be able to support your resource adequacy in your area? I haven't really talked much about this in the industry, but this is where I think that this forecast hosting capacity, which isn't widely done yet, will evolve to as we, progress over the next 5 years in a few places around the U.S. Next slide, please. So where we've gotten to in this discussion is then leading into this needs identification. So coming out of the planning analysis, then we get to needs identification and then the potential solutions. So we're going to end on this slide and have some clarifying questions before we then start to focus a little bit more on grid modernization, that green box there. Not to diminish anything else on this slide, but just for the sake of today's discussion, we'll then focus on the grid modernization. But basically, as you can see, these steps follow along what you all have been using as your basic steps in the planning process. So if we move on to the next slide, we'll open it up for questions.
Yes, thanks, Paul. Great discussion over there, presenting on the multiple objectives of distribution planning. As we look back at the process maps that the Silva cohort had prepared, this is a sort of like a cutout of the DSP planning, swim lane, and the IRP planning. One of the questions that I think some folks may be interested in knowing is, when we think about resilient distribution planning, what gaps exist in developing the planning criteria to inform a set of objectives that may be developed to, let's say, address a specific resilience criteria or metric related to a consequence or an event?
I think right now we've got techniques, as I've shown, like the threat assessment. We've got techniques like the bow tie analysis. We've got techniques to consider DER integration and different uses scenarios. What we haven't done yet, I don't think, is really sort of figure out how to tie these together sort of converge those in an analysis when we start to then look at the various needs that come out. So where I left off at the needs analysis, then start to look at a way to, which of those can, from a Venn diagram perspective, I should say, which of those overlap so that we can start to understand which of the potential solutions can solve most of the multiple needs that may have been identified. And from that, be able to then think about, feeding the second part, which is, what might then be the priority. But the first part is really translating those various planning analyses and needs into a kind of a uniform or unified sort of evaluation of those needs for where you're going to have overlapping, potentially overlapping needs in effect that would feed into your solution development, identification, development stage. So I think that's probably the biggest area, is how to do that. I've not seen this done yet, where that's done holistically. We've seen pieces of it, certainly parts of the resilience. We also haven't really seen the implication of, if we're going to be using distributed resources widely for meeting a lot of the resource adequacy, either as load modifying resources or actually energy producing resources off the distribution, then how do those need to figure into the resilience planning criteria or analysis? And because those will have also potential implications, especially if we start to extend to think about cybersecurity issues that may impact some of those resources. So this is going to get a little more complex over time, but I think certainly one of the areas that we've been exploring and discussing with folks in industry, in the Electricity Advisory Committee, and certainly with Mark McGranagan and EPRI, who'll be speaking, briefly at the end of my talk. We've all been sort of talking about this. I think there's some additional work to be done to kind of think through this and kind of come up with a good framework for it.
Mm-hmm. Okay. We have one question that came into the chat box. Would you like to have me ask that question, or wait till the end and the Q&A portion?
Oh, we can do it now, sorry.
Okay. So one question relates to the Mid-Atlantic Distributed Resources Initiative, MADRI. And the question is, can you comment on their integrated distribution planning guide relative to what you have covered today?
I'm not familiar with it, but I'm happy to, if there's particular aspects that somebody wants to ask follow-up questions during the Q&A, specifically about in relation to what I'm presenting, I'd be happy to speak to it.
Okay, I'll keep an eye out for that question, and please continue. Thank you.
Okay.
Sushma and Paul, 1 second. Commissioner Trumbold has raised her hand for a question, so let me unmute Commissioner Trumbold. Commissioner Trumbold, you're unmuted.
I'm sorry, I really didn't have a question. I think I accidentally hit the hand up, hand down. But Paul, thank you so much for presenting. I'm riveted. So I don't have a question, but thanks, Paul.
You're welcome. Thank you, Commissioner.
No problem. I'll mute you, Commissioner Trumbull, and we'll proceed with your presentation, Paul.
Thanks. So if we can move on to slide 22. Thank you. So as we shift our discussion to talking about solutions, grid modernization is one of the areas that obviously we've been spending a lot of time on collectively as an industry over the last decade, really kind of building off of what was done on smart grid in the 2000s. And I think we've gotten much clearer about the linkage between planning processes and modernization here as we think about a more holistic approach. And what I'm showing here is kind of a simplified view of the planning process that I showed earlier, where we have these kind of 3 time dimensions. So here we're talking about this in a time context that builds on the sort of functional boxes that were shown earlier. So here, starting at the bottom, we've got this distribution asset management, and that's a near-term focus. Usually that outlook is for the next year to 2, although that asset management or asset planning will inform programs that may be 10 years or so in length. And so, but the sort of near-term sort of action plan is usually a much shorter time horizon within the context of a longer programmatic approach. For example, things like aging infrastructure replacement. But this drives a lot of the internal budget process and prioritization that goes on an annual basis for work planning. The same thing with near-term distribution planning. Again, this is something that's typically done on an annual basis, as many of you know, and it also has a time horizon of about 1 to 2 years, really focused on very specific tactical activities that are going to be done. Usually this is within the context of a longer-term distribution plan, certainly within the context of a rate case, if there is in that jurisdiction rate case proceedings. These are activities that are done within that authorized amount that was identified in the case, or refinements based on changes that happen since that time to respond to customer needs or other kinds of changes that may occur. And again, this is very technically oriented towards workflow management and budget management. And these tend to focus on reliability, service quality improvements, near-term enhancements for load and DER. So you will get grid mod implementation dimensions as part of this, but often this near-term planning is a subset of a longer grid mod horizon, because, for example, software system implementations are much longer than typically 2 years from start to finish. So you will go through a couple of different near-term planning cycles for, say, a software system, let alone some of the more programmatic aspects that may be related to enhancing reliability. The longer-term distribution planning looks out over a 5 to 10-year horizon in most cases, although recently I noted that Excel's Minnesota went out 15 years, which is I think kind of an exception. Most are out 5 to 10 for the reasons that we were talking earlier about uncertainties. But this longer term is often done only every 2 years, in some cases every 3 years. I think given the work that you all have been looking at with comprehensive system planning, as we've seen in several states, there's an interest in aligning the time at which these are done, these longer term distribution plans, to align with the IRP and transmission planning processes, so that you've got these on a kind of an aligned sequence, so that one can feed the other, as we were showing. These processes feed into what we describe as a grid modernization strategy, that longer term plan, and then the nearer term tie into the grid mod implementation plans will have an interface with the near term distribution planning. Some of the asset management will definitely inform grid mod implementation plans. So for example, if you're going to be replacing a set of poles in an area and air switches to upgrade because of aging infrastructure, if you're going to be adding additional equipment on that pole, you would want to take that into account before setting a new pole that then has to be replaced because it couldn't take the load of what was being proposed in the GridMod implementation. So there is an effort to basically try and look at those and enhance what you put out under those asset programs to support the longer term strategies. The next slide, please. So just to go a little deeper, some of you have seen this in the presentations we've given about GridMod strategy and planning. This is really the basis for our volume 4, which will be out soon. It's in final review with the Department of Energy. So we have start with the mission and principles of a particular state or jurisdiction. That helps inform the objectives, scope, and timing for what's needed. And obviously there are elements that tie into the planning analysis we just talked about. Then there's a need to kind of look at grid capabilities and functionality. So what incrementally is required for the system to be able to support, given all the changes we talked about in terms of those multiple objectives. Then there's our step 3 is looking at the architecture and developing a strategic roadmap. When we think about architecture, it's how things are structured, including software systems and the IT piece, but also the grid itself. So as we think about more distributed resources, how should the control system be structured? How's the interface between transmission and distribution operators? What's the, how do we need to think about the structural aspects of the operational relationship between the DER provider and the distribution operator? So all those go into that sort of considerations in step 3. That then informs your GridMod strategy and roadmap, because then you develop some conceptual ideas about what kinds of technologies and the like may be needed over what time horizon based on longer term forecasts. And from that, you can start to develop some conceptual cost estimates and the like. So you can start to get a sense of, what may be involved and start to engage in a strategic conversation about, does this align with what the objectives of and interests of a particular jurisdiction? From that, ideally, you use that strategy and roadmap to then inform a more detailed implementation plan. And when we talk about an implementation plan, now we're getting very concrete, very detailed into an engineering analysis. So, and it starts with use cases and developing requirements. And the steps we're showing here on steps 4 through 7 are steps that moving into detailed design, technology selection, and deployment plan are essentially the kind of steps that EPRI developed with the IntelliGrid effort almost 20 years ago that have been widely used in the industry. There's some enhancements here that, what we describe only in the context that there's more, wider range of technologies. There's, greater number of things that, we're talking about with grid modernization to be able to support than where we were with just smart grid, better part of 20 years ago, but it's still very consistent. And we use and leverage a lot of that information in our references as part of this chapter, which is chapter 4 in the new volume. Chapter 3 is on the strategy. So that's the sequence, and we can go into the next slide. So one of the things that we developed for our one of our earlier volumes, I think it was in volume 3. We developed a generic technology stack, a way of representing the various technologies in a hierarchical form. That is, the technologies or infrastructure at the bottom is a prerequisite for the thing on top, and then sequentially as you go up this stack. We did this for a couple of reasons. One was to be able to sort of illustrate the relationship between different technologies in a very visual way. And the other was to start to really think about this idea of a platform that we've been discussing. And the idea around in the use of this term, there's two general types of platforms as people talk about. One is platforms for markets, and we're not talking about that. But we are talking about a platform that has common elements, common core elements, no matter what you want to put on top of that in terms of applications or things that you want that system to do. And in this case, certainly the physical infrastructure, physical grid is a core component. Operational communications are a core component. Sensing and measurement is a core component. Data management, obviously. And then we get into control and protection systems and analytics for operations, and obviously on the planning side in the light blue. So that's these components, both in the green and blue, represent those core elements that tie into what we see as foundational. Then above that are things that are applications, things that depend on that core, and but everything below the line you would need to run a modern system. Those things above are sort of optional depending on what you need and what you're trying to accomplish. Now, some have always noted that we've got smart meters and advanced meters, and the reason is that in a grid context, which is what we're looking at, smart meters and advanced meters are one option under sensing and measurement. Certainly they're needed if you want to do time of use or some other customer-oriented types of solutions. And certainly they can provide some level of grid sensing and measurement, particularly the advanced meters. And smart meters have obviously played a role in looking at outage management. But we look at those as optional. Those are ways that you can do it. There are other technologies that you can use as well. And so it's not to say that they aren't, but it's really, that's why we make that distinction. And same thing with pretty much everything above the line. They're all dependent on different objectives or requirements in a particular jurisdiction, and then choices that people may make with respect to how they want to address those needs. Next slide, please. Let's see. Okay, so the other thing that we developed both in volume 3, and then we expanded upon it to make it clear that working with E3 was Fritz Carl in particular, is expanding upon our thoughts on a cost effectiveness framework for grid modernization in particular, but it has implication for other kinds of distribution investments too. And that is, there's really 3 categories. One is best fit reasonable cost, the second being benefit cost analysis, third being customer self-supporting. Customer self-supporting is things like undergrounding or the like, where a single customer benefits or a new service extension or some other special facilities that may be required for a particular customer, but doesn't benefit any other customer. So those are pretty common in most jurisdictions to have some form of that, but those are sort of the exception. Most of what we're talking about will identify either the best fit reasonable cost or benefit cost analysis. And the reason that we started to look at best fit reasonable costs and trying to think about that application is because that if you're looking at core platform, the core platform has 2 unique challenges when thinking about economics. One is that those core platform elements support multiple potential uses and therefore benefits, some of which are operational savings, many of which are supporting societal objectives, policy objectives, or customer choices. The other is, so it's very difficult to do a mapping of one-to-one, particularly if things haven't been identified yet. So they're kind of, they're known, but we don't know exactly when they're going to occur, and we don't know exactly the shape. So therefore, we can't really put specific numbers on it. The second problem is that comes in is that some of those investments occur over a period of time, and often outside the potential time window at which the application is initially asking for the start of an investment that may span over a period of time. So how do you tie these together becomes quite challenging. So there's supporting multiple benefits, not all of which are entirely known and quantifiable. And the second is the fact that we've got timing mismatches with some of these investments as well can be problematic, where part of the investment is covered in the platform is covered in one time period, say infrastructure, and then the communication comes later, and they're not all packaged as part of the same, which happens fairly often for these kinds of things. So that becomes quite problematic. And we've seen some states, sort of acknowledge that challenge. California in particular had a fairly good explanation of the challenges they faced when they tried to address this in a cost benefit, these core components, and found that it was next to impossible to try and do in that context. Now, there are elements of grid modernization that very specifically do tie to cost, benefit cost. And in these cases, they are the cost related to the benefit of what is being proposed. For example, time varying rates, there's a benefit associated with that. The cost is what you may do in terms of smart meters to implement it. Same thing with other utility programs around demand side management. And certainly as we think about any DER policies that may be in place. So for example, in California where you've got, new building codes requiring solar panels on every roof, that's going to have an implication for what the grid may need to support. And therefore, that benefit would have already been identified or, at least in public policy, it's been codified. So, and then NWA procurements may trigger some additional investment, for example, a DERM solution, distributed energy resource management system, to be able to support. So in that case, it's a cost to support the benefit of the NWA or other utility programs that it might be supporting. So that's the context here. Next slide, please. The net of that is we pull these all together into a long-term roadmap. And in this case, as I mentioned, Excel had a 15-year horizon. Most would go out 10. But you can see there's a logical sequence about how these different investments integrate over time, one building on the other as you sequence them. And there should be a logic that threads through why you do one before the next and so on, and how these link up over time. And in some cases, as we've talked about, it's going to take many years to do a full deployment and when I say full, it may not be the entire system. It may be a subset of the system or certain customer types or certain geographies, and those should all be clearly identified and developed as we go through. Next slide, please. So here, stepping back, as we think about solutions, and often we've been discussing non-wires alternatives for grid investment, particularly infrastructure type investments. The other thing that we should be thinking about holistically is how do we think about a portfolio of resilient solutions? And one of the things we've been kicking around is this idea of this 2x2, which is on one dimension, we're thinking about the societal benefits. So what might a resilient solution for an individual customer achieve from a societal benefit versus a solution that addresses all customers? And that's the extreme. But this gets more nuanced when we start thinking about subsets of that, whether a single critical facility, depending obviously what type, all critical facilities and essential services. And then the other is, how do we think about the potential solution scope? In many cases, those below the line in the lower two boxes are really point solutions. They may be backup generators, they may be a customer microgrid, something of that sort, or something more localized. But then we have these community-based solutions where we're looking at a whole residential community where we're talking about then these multi-user community microgrids, or an entire neighborhood where we're talking about maybe these mini grid concepts where you're getting even larger, an entire town which might extend the mini grid, and then you have all customers where you're now really looking at a very pervasive set of grid and combination of microgrid solutions to kind of really address resilience for all customers. So this idea that there's a whole range of these potential solutions, and how do we think about optimizing this between what the utility might do and what customers may do, what legislatures may through law require for critical facilities or even individual customers, as we've seen in Texas and Florida, for example, and how does that relate to what the utility ought to be thinking about or communities thinking about with respect to kind of neighborhood or larger scale. So there's a need to really think about these things, because right now in many cases they're kind of going on concurrently without necessarily looking across those to see is there an optimization happening. One of the things that's particularly hard to get a view on is just the uptake on an individual customer level. How much backup generation, whether we're talking about stationary or portable, which has been growing at nearly 10% on a compounded average growth rate for the last decade, and now increasingly energy storage, as that's gotten very inexpensive, relatively speaking, that's almost like an appliance now, and people are putting those on at an increasing rate just to address resilience. So one of the things I think we're all challenged with is where are we heading over the next 5-10 years as technology advances, and what does this look like to really address resilience needs, given that you've got a lot of individual customers and communities sort of self-supplying their own resilience in effect. So just a thought to pass along. That leads into our next slide, which really talks about who all needs to be involved and is increasingly involved in these discussions, whether we're talking about at a very localized level, or we're talking about something at a kind of a larger level within a particular jurisdiction, particular utility, or then we're talking about something that's a major regional crossing multiple states and the like. Who all's involved in these different discussions about thinking about both what the impacts are and then what the potential implications and considerations in the planning process ought to be. Next slide, please. So as some takeaways in thinking about the resilience dimension in particular, how are potential threats being assessed and translated into planning considerations? Is there a clear logical explanation of how a proposed investment directly or indirectly supports resilience? This, I think, is going to be more challenging to unpack. Is there sufficient transparency in the distribution planning process to understand how resilience is being addressed and reflected in investment plans? So how do those threads, going from threat assessment all the way into budgets, and realizing that resilience, as I showed earlier in the pie, covers 95% of touches on 95% of usually a capital budget. How are those threads aligning? How are grid investments and customer independent solutions, as we were just talking about, being considered as part of an overall resilience portfolio from a state or jurisdictional perspective, or utility perspective? Are all of the key stakeholders involved in an effective engagement process? So what does that look like? Do you have something akin to what I was describing that's going on in Hawaii, or have happened elsewhere, earlier in the Mid-Atlantic and Northeast, based on Superstorm Sandy and some of the other hurricanes down in the Southeast? So I think that's my last slide. Next slide, please. Yeah, and here's some references. The Michigan IDP order, I think, is useful because it kind of set the example of one example of how to think about your starting point for distribution planning and resilience in particular. The PG&E wildfire mitigation plan, I think, is useful to kind of see how they've applied the bow tie analysis to then think about prioritization of investments to mitigate that potential issue, both prevent and mitigate. The Excel 2019 IDP is a pretty good plan to kind of look holistically at how they're tying many of the distribution planning dimensions we talked about in this discussion. The other is that the HECO's resilience planning effort shows the engagement they did in the discussion that they had with their stakeholders through the working group process. I was looking for another example of this. If you have some that are publicly accessible, that would be great. We would look forward to hearing it, and we can use those as references in upcoming materials that we can highlight. Thank you for your time and attention.
Thank you, Paul. A wonderful presentation. You gave us a lot to think about. We have a couple of questions, and in the interest of time, I'll start asking them if that's okay.
Sure.
Okay, so the first question is the phase out of SF6, sulfur hexafluoride, and PCBs part of an integrated distribution plan?
That would be usually done through the asset management planning as part of the infrastructure. It's not strictly speaking aging infrastructure, but in effect it falls under that. So those pieces of equipment have to be replaced, and so that'll be part of an asset management plan. And so that's one of the things we're highlighting, is the need to take those into account within an integrated distribution plan. In larger utilities, the group that does asset planning is not often the same engineering group that does the rest of the planning that we're talking about. They're not the same group that does grid modernization or system expansion or upgrade. analysis. So increasingly, I think there's a recognition that those two groups need to, to work together to have a cohesive distribution plan. They do report up often to the same executive level, but that's an area that we think would benefit from greater integration. We do see that in some of these plans, though. For example, Excel's plan, I believe, touches on the asset management stuff.
Mm-hmm. Okay. How much resiliency planning or coordination do you see between different BA or even states?
Between the states, I couldn't speak to that. Within the utilities, I think there's a lot of best practice sharing that goes on in terms of how to think about this, but and Mark may be able to speak to it a little bit more directly, but I would say that because they've had a number of efforts on this over the years, in addition to what they're currently doing. But I would say that the link between the resilience and the rest of the distribution planning, I think that's an area that there's further enhancements that can be done.
Mm-hmm. Can you explain what is meant by distribution voltage upgrades under stage 2?
So voltage upgrades, so as we get into stage 2 on the curve represents a pretty significant level of DER, particularly solar and increasingly storage on the system. And that variability in how those systems are used and their effect either on modifying load or export into the system will have a pretty significant impact on voltage, as we've been talking about. Even with advanced inverter technology, you still have a voltage management. You still, with that capability, you still have a need to be able to interact with those to enhance the and maintain voltage. And essentially, there's a need to coordinate the voltage and those devices that may be responding to voltage changes in voltage, like an inverter. You have to be able to coordinate that with load tap changers and regulators on the rest of the distribution system, so that you've got those operating in harmony. Otherwise, you're going to have things like one moving in one direction, the other, of course, counteracting to go in a different direction, called hunting, and you can have that sort of you can create some instability in effect. It's not instability, but you can create a lot of havoc from a power quality standpoint at that level. So as we get more and more devices out there, it's going to be more important to really kind of understand how we coordinate the operation of those different devices. That's really what that's getting at.
Mm-hmm. Okay. Other than granularity, would there be differences in the forecast for IRPs and DSPs ideally, or is it possible as a practical matter?
It's not really necessary for the IRP to have the level of granularity that is needed for the distribution level. I think it would be I think it would add a level of complexity and time that you wouldn't, particularly if you're talking about a jurisdiction with multiple for system level forecasts for a particular area that may involve multiple utilities. Trying to gather that local information, which often involves interviewing large commercial developers or commercial customers or residential developers or local cities and the like, to understand what changes may be happening. And some utilities are getting pretty sophisticated with how they're thinking about forecasting EV adoption and the kinds of folks that they're talking to. That gets pretty time consuming, and I'm not sure how that would tie into at least the forecast planning period that you have to develop a forecast, which is often about 6 months. So it's not clear that you could get all that done within that window. And generally, you want to use that system forecast to then work off of and just look at adjustments at the distribution level. So I think it could be practically, an additional level of, time and effort that may disrupt what you want to do in your process flow in terms of time that you have allowed for developing a forecast.
Okay. Those are the end of the questions. I'm going to ask our organizers to see if there are any raised hands that we want to ask folks to unmute.
Hi, Sushma. No, I don't see any raised hands. Thank you.
Okay. Paul, thank you. And if what we can do is provide the slides and get folks your contact information, and they can reach out to you if they have any additional questions.
Great.
Thank you, Paul.
Was Mark going to share a few thoughts?
Yes, I was going to ask folks to hang on for a few more minutes. We have a special guest, Mark McGranagan from EPRI is here to tell us about his project. Mark is the VP of Innovation at EPRI. He's worked in the power industry for over 40 years and has been involved with EPRI for the last 17 years. He's been an innovator in the areas of distribution planning, reliability, resilience, and power quality for all of this time. He's actively working with electric utilities and industry organizations around the world. Mark is leading a new effort at EPRI on valuing resilience, and he's here and would like to say a few things about it, including an invitation for NARUC NASEO to engage in this EPRI project. Mark, I think you might be unmuted already.
I clicked the button anyway. Really appreciate that, Sushma, and appreciate the invitation to just say a few words before we close down here. First of all, I want to thank Paul. It's great to be able to participate in this overall effort. We've been working with Paul and Jeff Taft and Joe Palladino on the DSPX effort. They've been great to coordinate with. We did a roadmap together for First Energy to get input to the process, and we've used the process that Paul outlined to help a number of utilities with their grid modernization roadmap. So I think it's been extremely valuable to the entire industry, and taking on this next task of where resiliency fits into that whole planning process, maybe one of the most complex parts of the whole effort that we've had. So I'm really excited about that. And what we have an effort at EPRI that we're starting as an industry coordinated effort that's perfectly right in parallel with the effort that Paul described. We call it the Value of Resilience Interest Group, and it's designed to be a 6-month effort, very focused to get as many stakeholders as we can get at the table, work virtually to address topics around metrics for resilience, and try to talk about the gaps that exist in valuing resilience for exactly the reasons that Paul described, of the difficulty of incorporating resilience into the planning process, whether you're working on common investments, platform level investments that cut across many applications, or you have investments that are focused directly on resilience. The value of resilience goes into those justifications, no matter how you look at it. So we've got together, I think we've got 40 some utilities that are at the table now, of which almost half of them are international, because this is an international issue. There are IOUs and co-ops and munis and federal utilities. Joanna Zetterberg is helping coordinate the DOE coordination and the Grid Modernization Lab consortium of all the labs. I look forward to working with Paul and Jeff on this as well. I think there's going to be some real information opportunities. And what we're going to do is just basically have monthly webcasts with assignments in between to help get people's thoughts together on this topic, and try to, before the end of the year, produce a gap analysis and a roadmap, at least for addressing the value of resilience question. And that'll give DOE and EPRI and others some direction in terms of plugging resilience into the planning process from a local level, individual level, societal level, and I think the curve that Paul showed around kind of the 4 quadrants and dealing with point solutions versus global solutions, and you know, the level of criticality of the customers involved is right on target as the kind of thing that we need to talk about in an interest group like this. So very excited about this effort. Our first webcast to kind of lay the groundwork and get the assignments out there is in June. I actually can't remember the date to check that, but Sarah Mullen Trento is she's our leader in charge of this effort at EPRI, works in our technology innovation space, and is organizing this first webcast. I think she just tried to text me the date, but I didn't get it. Went right by me. Anyway, we'll share that in the notes to this webcast. So thanks for the opportunity to say a few words. Really looking forward to the coordination.
Thanks, Mark. I'm assuming the organizers will pass your contact information and anything related to the attendees.
Yeah, great.
So with that, unless there are any other questions, we are exactly at 3:30, and we'll close the webinar. And thank you for your time, and thank you again to Paul and Mark for giving us your insights on this subject. Have a good day.
Have a good one. Thank you very much.